I'm not a mathematician, I'm in an engineering department. I have a background in condensed matter physics, computational materials science. I've tried to pick out a focus on methodology and on things that I hope will be of interest to mathematics, with a sprinkling of applications to show capabilities and challenges, and a particular focus on techniques for scale bridging to align with the theme of the workshop. By way of motivation, in my group in Warwick, we're interested in what we call chemomechanical processes, so things that involve concerted action of local chemistry and long-range stress. So prominent examples include fracture, where we're breaking individual chemical bonds, and this needs to ultimately be described with something like quantum mechanics, because we're breaking a bond, pulling electrons out of it. But at the same time, we need to model very large-scale systems so that the boundary conditions don't completely determine the result. If we simulate only 100 atoms, then we can't really adequately describe fracture. Other examples include friction. So this is an AFM tip sliding on a surface. Again, local rearrangement of chemistry, but long-range interaction and strong coupling with stress. Or plasticity. This is a super-alloyed turbine blade for a jet aircraft, which is a single crystal of nickel with nickel-free aluminium precipitates, and we're interested in engineering the material to control the plasticity response to prevent dislocations from entering these precipitates and adversely affecting the ductile response of the material. Another example is plasma-facing materials for nuclear power stations. So there we need to have materials which can withstand the immense flux of heat and energy that you get from a reactor core. Tungsten is the only material that's up to the job, but there's a lot to understand about how it interacts with hydrogen and helium, for example. Another prominent example that sort of inescapably involves chemistry would be hydrogen embrittlement. So we've got a nanoscale crack tip in something like iron. Hydrogen is diffusing around inside the material, getting to crack tips and causing stress corrosion fracture or subcritical crack growth. And so we can't really avoid the need to describe chemistry at the same time as mechanics. What tools do we have in the toolbox that we can potentially apply to this? So this is my version of the multiscale picture that we've seen many times. I think I made it quite a few years ago now, so probably we could add an order of magnitude to some of the values on the x-axis, but the ordering is comparable to what we've seen elsewhere. As a starting point, we might think of using interatomic potentials, and until recently, this was quite challenging for predictive accuracy in these kinds of materials problems, simply because the models were a little bit too simple and therefore not sufficiently transferable. So here's an example for fracture. This is a brittle material, this is glass. Actually, here we have silicon, this is silica, but similar material responses would be expected. If we look in an experimental image, an AFM image, we see that the crack should be mirror smooth and atomically sharp right down to the very tip. And this is on the nanoscale. If we look at the comparison between a continuum model, where we expect stress to diverge as 1 over square root r as we approach a tip, and an atomistic calculation, we see perfect agreement beyond a couple of nanometers ahead of the crack tip. So the process zone in a perfectly brittle material really is nanoscale. We only really need to describe nonlinearities in a very small region, and so there's hope for doing that with an accurate method. However, if we use a simple interatomic potential of the kind that Christoph mentioned earlier on that involve two and free body interactions only, we don't correctly describe the dynamics of fracture. We massively overestimate the amount of energy that we have to put in. We don't recover this mirror smooth surface. We get emission of dislocations erroneously. We get a lot of mess, essentially. And I'll talk about some ways to remedy this, either by improving the quality of the potentials or by augmenting the description locally with something at a higher level than this description. We can make useful contributions to understanding material science using quantum mechanics alone, using density functional theory, if we choose the quantities that we calculate in a smart way. So again, thinking about fracture, we know that there's a global energy balance criteria going on. Griffith tells us that a crack moves forward if the energy that we relieve in some column ahead of the crack tip exceeds the cost of creating two new fracture surfaces. So we can use a kind of scale bridging type approach to directly compute the cost of creating those surfaces and then use the thermodynamic energy balance to say that that's the energy that corresponds to fracture. We did this in silicon carbide a few years ago, and we had to take account of the local chemistry in that there are different polymorphs of silicon carbide, different possible surface terminations, and you need to kind of take all those things into account. But that's all possible within the couple of hundred atoms that you can fit into a density functioning theory calculation. So you can do a few of these calculations, you can calculate surface energies, and thereby make a prediction that's reasonably accurate for the fracture toughness and that compares well with experiments. These were experiments done by Finn Giuliani at Imperial, double cantilever slow crack growth. So the crack grows over hundreds of seconds, it's kept stable, and therefore you can accurately determine the fracture energy, and it's in pretty good agreement with what we calculate, directly estimated from the surface energy. However, these kinds of calculations can't really give us insight into mechanisms. So we can compute surface energy, we can understand how it relates to the measured fracture toughness, but we don't have a mechanistic understanding. If we want that, then we need high precision. We either need an improved interatomic potential that can directly describe mechanisms, perhaps using machine learning type approaches that we've seen earlier on from Gabor, or we can augment the description locally. So we can use simultaneous coupling of quantum mechanics and classical interatomic potentials. That means that we can afford to have 10 to the 5, 10 to the 6 atoms described with a simple model. That's sufficient to capture the elastic relaxation and the long-range stress concentration. And then only where and when we need it, we can augment the description with a higher level method, in this case, density functional theory, which does correctly describe bond breaking in a wide range of materials. If we do that, then we recover the mirror smooth fracture surface behavior. We actually also see we get some quantum mechanical effects in the reconstruction of this surface. So you can see we have alternating pentagons and heptagons along that surface rather than just the pure hexagons that you get with the classical model. And that's because electrons are delocalizing along the surface, they're pi bonding, and so we're getting a different response, and that does affect the fracture properties that will be relevant at larger scales. So the way that this approach works, essentially, is that we compute forces on a quantum mechanical region, we combine them with forces of sufficient accuracy elsewhere in the system, and get an overall set of forces that we can use to advance trajectories. We can put as much chemical complexity as we like into that near tip region without having to do any reparameterization, because it's a first principles ab initio method, so we can look at things like stress corrosion, where there are chemically aggressive species, water, oxygen, etc. around, or we can put impurities in without having to refit models and take advantage of the transferability that's intrinsic to the quantum mechanical method. However, we're a bit stuck in terms of timescale. The clock is set by the cost of doing DFT calculations at every step. Okay, the biggest approximation that we make is deciding where we're going to put quantum mechanics. We need to think about how to do that. As I said, ideally, we'd like the whole thing to behave in the same way as if we simulated the entire system with quantum mechanics. That's not feasible, but because of nearsightedness, because of locality in practice, we can obtain a good approximation to that. So if two atoms are far away, because of screening processes, they don't actually talk to one another, and all derivatives of experimental observables like forces go to zero. So we can often identify regions where interatomic potentials are likely to be insufficiently accurate using topology, at the tip of a crack at the core of a dislocation, or we can use other criteria. So this is a piece of work we did a couple of years ago, looking at pulling a nanotube out of a polymer composite. So we've got a nanotube here, we've got a polymer composite, and here it was the interactions between all of the polymer molecules in the nanotube where the accuracy was likely to be insufficient. We could flag that looking at the local per atom energies predicted by the interatomic potential, and where those exceeded some threshold, we said we probably don't trust it in this high energy regime, and we placed a series of clusters at all of those contact points and computed them in parallel. And Magic?
Yeah, so for crack surface, if you do some tests,
yeah,
then it makes sense to have QMM region and like a small tube around the surface as well. Or
you mean back behind the crack?
Yes.
It's not so critical for determining the kind of subsequent fracture response, because that surface is no longer.
Yes, but you said like there's different, qualitatively different behavior with the surface relaxation.
Yeah. But once the crack has advanced, that kind of surface behind is almost irrelevant in determining the subsequent evolution. So the reconstructions that come off the tip are definitely very important, but things that happen later on are potentially less important. So in this case, you're just treating those contact points with actually a low level of quantum mechanics. This was just type binding. is sufficient to capture the overall stress strain response. So if we just use classical, we massively overestimate how hard we have to pull. It's very hard to break the bonds with the green curve. If we do the whole thing with tight binding, we get a certain critical stress. And if we treat only the contact points, we get the same thing, but at much reduced cost. Recently, some work has been done by Yang Shui, Wang and Christoph's group, and together with Lei Zhang as well, to try and formalize this a little bit more and come up with automative ways to decide where to place the quantum mechanical accuracy. And the idea is if you've got a fixed budget of computational costs that you can afford 500 quantum atoms, where do you get the best response from placing them? A couple of applications to show you what we can do and what we can't do with these approaches. So this one is a fracture of diamond rather than silicon. We're zooming in on a crack tip here. First of all, in pristine diamond, here we see again mirror smooth fracture surface creation. Bonds break one by one and the crack advances. And now we can look at what happens if we place just one substitutional nitrogen impurity ahead of a crack tip. And we can see what happens within the quantum region without any reparameterization. We get interaction between the propagating crack and that impurity, and it causes the crack to systematically take a step up by one cleavage plane. If this happens many, many times, it leads to experimentally observable surface features. So these are new experiments done by Andy Jardine in Cambridge. And we see if there aren't many defects around, you get a small number of these ridges. If you increase the concentration of defects, you get many more of these ridges, strongly suggesting that what we observe in the simulations explains the experimental surface response. We can go a bit further and build a simple model based on what we see in the QMMM simulations, and we say that steps initiate at sites proportional to the concentration, and we get images in reasonably good agreement with the experimental observations. But a big challenge here is that these are very expensive calculations and that we can only do short duration simulations. So it would be better to try to incorporate information from the density functional theory calculations into improved atomistic models so that we don't have to keep calling it. Especially when you look at a simulation like this, you can see it's doing the same thing again and again. So it's a little bit wasteful to keep calling quantum mechanics.
Okay.
Yep.
So in terms of the simulation, is it just really the budget that you have computationally is just not sufficient to go to long time scales, or are there any stability issues like longer term?
No, it's really just the budget and the fact that it's serial, that you have to do one step after another. Yeah, Gabor.
So of course, can you go back one slide?
Yeah.
These are reminiscent of what happened before in silicon.
Yeah.
In the earlier work.
Yeah.
But the geometry, go back to that.
Yeah, sorry, I have to wait for the movie to finish before I can advance again.
But the geometry is different, right? So
the images are inverted compared to what you're used to, so the geometry is pretty similar. This is 111.
But is this also 3-point bending or 4-point bending?
No. So this is less controlled fracture testing, as diamond is much harder to do in a controlled way.
Yes, so I mean the experiment. So, but that's really nice, right? Because in the 3-point bending earlier stuff, you had these images, but it was a very different geometry. And
Yeah.
in fact, they get the same correlation.
Yeah. It seems it's real.
Different geometries.
Yeah. Okay, so the simulations I showed you so far were all quasi two-dimensional. The fracture crack front line was quite short, and that was a little bit limiting. So I want to tell you a little bit about some work that's been done with Petr Grigorev and Tom Swinburne. Some of you might have seen a poster about this outside a couple of days ago, so I won't spend too much time on it, but it's a really nice idea because what we do essentially is take the kind of simulations that I've shown you just now for cracks, apply them also to dislocations. This is a screw dislocation in tungsten, so relevant for the plasma-facing applications that I mentioned. And then try and incorporate basic ideas about what happens in this system in an improved version of the embedding potential so that we no longer need quantum mechanics just to do dislocation glide, and we can use it instead only where we have complicated chemistry as well. So that's the motivation, to try and do a constrained update of the potential parameters so that we can have a long dislocation line fully described by the machine learning potential, and at one point along the line we can put impurities and describe those with quantum mechanics. How does it work? Well, we do some reference calculations with the existing method, and we look at the glide barriers for dislocation motion. So we work out how easy it is for dislocations to move from one side to the next. That gives us a bunch of reference configurations, shown in black here. Originally, the potential on its own is not able to describe those environments adequately, but what we can do is take those black minimum energy paths and use them to update the potential parameters. We have to do it a bit carefully because we need to preserve some properties of the potential so that it's still suitable for embedding. In particular, we have a hard constraint on the elastic properties to prevent reflection of phonon waves at the interface between quantum and classical regions. We need to have a really good elastic matching there. We also use some soft constraints to generally prevent the potential from changing too much when we update it. And this works well. You can see after retraining, the potential alone describes the glide process very well. And so then we can go on and do some more interesting science with it. So what we wanted to look at is what happens if you put helium near to the dislocation. We did this first of all in this 2D geometry, and we found quite a sort of startling result that the helium completely changed the core structure. It moved the dislocation from one of these upward-pointing easy core configurations to the adjoining hardcore downward-pointing triangle here. But of course, that's a bit of an artificial simulation because effectively we've got a long line of heliatoms across the periodic boundaries. So with the new capabilities, we can instead have a very long dislocation line with just one helium, or maybe 2 or 3 heliums to investigate concentration effects. And we can see what happens there. Of course, far away from the defect, the dislocation stays just as it was in the easy core configuration. Locally, it changes, but not quite as dramatically as when you have an entire platoon of helium there. Okay, so that's actually quite a nice example of combining some simultaneous coupling in order to bootstrap an improved hierarchically improved model. Now I want to come back to fracture for the last example on this concurrent coupling. So just a kind of brief review of the energetics of fracture for those who are a bit less familiar with it. In a continuum setting, cracks propagate because it's energetically favorable to do so. So because the cost of opening surfaces is less than the strain energy release associated with unloading the material. When we put atoms into the picture, things are a little bit more complicated. The crack is now metastable at each atomic site along the crack front, and there are energy barriers that have to be crossed. And as you pull harder, this whole energy landscape tilts downhill, and those barriers get a little bit smaller as well. This is a very old idea dating back to Sinclair and Lorne in the 1970s, but what has been challenging is to quantitatively calculate how these barriers are determined for a particular material. Whether their material properties and how they vary as you vary the applied load. So you can do this a little bit with QMMM. You can do expensive calculations, and this is on 110 plane in silicon at a lower load than what I showed you before. So the crack is propagating slowly. It's firmly activated fracture, essentially. Every now and again, it gets trapped in one of these sites here, but it's expensive to do that with dynamics, and it's much better to try and directly compute minimum energy paths. So together with Tom, we did this a few years ago. We can relax configurations, we get minima, and then we can join those minima with a chain of states and relax using what's called nudged elastic band to get them a minimum energy path for this process, still using quantum mechanics near to the crack tip and a classical description far away. We can then repeat that at a variety of different loads and see how that lattice trapping barrier goes down as you pull harder, and find the range of stable loads at which the crack is metastably tracked. This is still quite expensive. It involves lots of calculations, and it's rather fiddly and error-prone to set up these initial guesses for the chain of states. So I want to tell you about some work that helps to...
Sorry, can I ask a question?
Yeah.
So in order to compute the barriers, you actually need setup points, right? So minimization is not going to...
It's a nudged elastic band calculation, so that's a way of finding the transition state. I can say a bit more about it if it's useful. But so we have a minima at the two ends. We join them with a chain of states. We have springs that connect those minima. And then we relax the entire chain with the springs ensuring that the images stay well spaced. And in that way, we relax to the full minimum energy path, including the transition state. So it's quite a well-established method, but maybe not outside of atomistic modeling. Okay, so I want to say a little bit about an approach that combines an atomistic description of the crack tip with a continuum far field condition. And this is work with Maciek Booz, who's participating in the long program. I think some of you will have seen Maciek talking about this in a seminar a few weeks ago. So I'll focus more on the applications to material science than the mathematics. We first actually did something a bit more ad hoc. So this was fracture of amorphous carbon. We have a giant piece of amorphous carbon. We apply a continuum linear elastic boundary condition to the specimen, and as the crack advances, you can see it wiggles around in quite a complicated way because it's not a crystal anymore. There isn't a cleavage plane, and so it's a more complex response. And what we had to do in this case is fit the crack position as we observe these dynamics and move the center of the continuum field in a bit of an ad hoc way. And that was a little bit unsatisfactory, but actually in terms of practical outputs, it was quite useful. If you look at a zoom in of the crack tip here, you can see we've got a kind of quasi-brittle behavior. So it's like a ductile material. We see formation of voids, coalescence, and so on, but right down on the nanoscale where we can investigate it with atomistic modeling. So it's quite a nice playground. This process zone is on the nanoscale. And we can actually, again, make fracture toughness predictions in good agreement with experiment. So by varying the density of the specimen, by looking at different sizes of sample, and by extrapolating to large samples, we can come up with a range of stress intensity factors that agree pretty well with known experimental measurements for amorphous carbon. But as I say, the unsatisfactory part, particularly from a mathematical point of view, is having to somehow determine where the crack tip is. And you can see in this picture, it's not very clear what the point that you would identify as the crack tip would be. So this is the work with MagCheck, building again on ideas from Sinclair from a long time ago. And the idea is to introduce flexible boundary conditions. So we have an atomistic domain, but we surround it by an infinite continuum description. And we then see how big we need to make that atomistic domain in order to adequately capture fracture. And then the novelty of the work with MagCheck I'll talk about in a minute was to combine this with a numerical continuation approach. But first, a brief overview of the flexible boundary conditions. So the idea is we have crystal positions, we add continuum linear elastic displacement field with a given stress intensity factor K, and then we allow atoms to relax just in this interior region 1 here. The outer regions are just there to couple with the continuum. We can write down a total energy for the system with contributions from the atomistic part and from the continuum part. That's parameterized in terms of position of the crack, which is just a scalar alpha, and the applied far field stress intensity factor. And then if we take a derivative of this total energy with respect to this crack position, we can get an effective generalized force on the crack tip. And it turns out that this just involves summing up atomic forces multiplied by derivatives of the continuum linear elastic displacement field, which we have analytically, and so we can do. So we can use that to drive the extended system. We have forces on atoms that we can use to drive the internal degrees of freedom on the atomic part of the system, and then we have this generalized force that drives the crack tip. Okay, so that was the method as originally proposed by Sinclair. It's been extended and used in other contexts, particularly for dislocations by Dallas Trinkle and others. What we did, or what MagCheck in particular did, was combine it with numerical continuation, so that once we've got one stable equilibria that satisfies 0 atomic forces and 0 crack tip force, we can find another one nearby by introducing an extra equation to close the system and allowing us to map out solution paths, bifurcation diagrams for fracture, essentially. So let me try and explain how that works. This is silicon again, 1-1-1 cleavage plane. And these are the solution paths that we get. I think I'll start the movie while I'm talking through it because it takes a little while to play. So here we're following a solution path. This is the crack position. You can see the crack position updating in the movie at the bottom as well. Now we're on the stable part of the bifurcation diagram of the solution path. So the crack position is increasing as the stress intensity factor increases. That corresponds to the successive green, orange, and purple portions of the graph here. Under standard conditions of a fixed stress intensity factor, fracture would correspond to jumping vertically in this diagram. So you'd move forward in crack position at fixed K, and you'd have to pass through a transition state here to get from one minima to the next one. So the dashed part of the diagram maps out the unstable parts of the solution path. And the nice thing about the numerical continuation is that it can follow round the folds in the bifurcation diagram and continue to find equilibria that are saddle points as well as minima. Okay, maybe I'll just go back in the movie a little bit because there's an interesting feature just a little bit through the diagram. So as we go round the stable part of the solution path, we see a bond slowly opening. I think it'll open completely when we get to the top there, the way that I've chosen to visualize the system. So the correct position is smoothly moving forward, and then the bond is going to open. And then there's this interesting feature down here in the unstable part of the solution path, which corresponds to the bond behind the crack tip. So you see that this bond has opened already, but now keep your eyes on it as we go through this kink here, and you can see a further relaxation, and that's because there's a many-body potential. It's not just a nearest neighbor interaction, so there's still some interaction there, and we see that finally kind of giving up as we go through that kink in the solution path. Final thing to tell you about on this slide is the energy landscape associated with this set of solution paths. So we do one long calculation, and we map out the whole thing, and then we can read off all of the energetics and all of the energy barriers from that calculation. So if we take these solution paths and compute their energies, we find they all cross at a load here where it's neither favorable neither to advance nor to retreat. That's the Griffith load. It doesn't exactly match the estimate of the Griffith load that we would get from the elastic constants, probably because of finite size effects in this case. That's something to investigate a little bit more. If we go to the right of that, it's favorable to advance, so purple is below green. If we go to the left, it's favorable to heal, for the crack to go backwards, so purple is above green in this landscape. Okay, so I couldn't resist showing you some pun intended breaking news where we've extended this approach to a more realistic materials model. So this is iron. You don't think of iron as a brittle material, but at low temperatures it is, and that's a big problem. There's a brittle ductile transition below which you're at risk of getting fracture, and that's relevant for civil nuclear reactors, for example. So this is using a machine learning potential rather than the previous results I showed you is quite a simplified potential, albeit one that does give a brittle response. So this is a potential fit by Lei Zhang and involving Gabor and Francesco Maresca from Groningen, using the ACE scheme that we heard about from Christoph in the previous talk. And we've managed to get it working with this numerical continuation scheme. You can see I'm taking rather big steps here, so it's not as nice and smooth as the previous result because the potential is much more expensive. That's something that we can further refine. But the good news is that it basically works. We get the solution path coming out very nicely. We can see the crack advancing, rather a sharper crack tip here with the metallic bonding associated with iron rather than the covalent bonding that we saw before where bonds were more tightly defined. We're going round the loop. We're going to start jiggling along this next part of the diagram now. But the really appealing thing about this is that all of the subsequent crack advance steps are similar to one another, and that shows that our atomistic domain is big enough that we're capturing finite size effects pretty well. We can look at that a bit more carefully. We can make the atomistic region bigger and bigger, and we can look at how our estimates for the range of stability change. Is somebody laughing at the jiggly thing going backwards and forwards a little bit? Yeah. So we can look at the upper and lower limits of lattice trapping, and we can see that they actually converge quite well as we go up to 100 or so angstroms. Yes, questions?
Interesting how you can handle the magnetic spin of iron next to the crack.
Yeah, no, we haven't modeled that here. So it's an interatomic potential, which is trained on density functional theory data that does include spin, and then we've course grained out the spin when we fit the potential. So we're not capturing
on defects, or
yes.
And then you have the spin configurations. That's very, very.
We're integrating out the spin effectively. That's what we're doing for now. Of course, it'd be better to include magnetic degrees of freedom in the potential as well. But yeah, I think there was one, Lev. Yeah.
How you drive this system? What are you changing in terms of loading to make the crack move?
So we're following the stable equilibria along the solution path. That means
I'm a bit surprised that it's a smooth transition. There is no jumps. There is no kind of subcritical branches there, because usually when crack moves, it either emits acoustic emission or creates a heat. So there are some kind of discontinuous processes must be there. And for you, everything is very continuous.
this is zero temperature.
That's about the unstable branch change.
Yes.
So the unstable branch is fully captured here. So this would not be mechanically stable along this branch here, but because of the numerical continuation, we're able to follow onto that unstable branch.
So in terms of real controlling parameter, there would be jumps, yes?
So you would just, sorry, because I worked on this, you would, if you didn't include this nice continuation idea, once you pass a certain K K, the stress intensity factor, you would just jump onto the next stage of it, whereas we are able to trace out all the subtle points in between.
Yeah.
So I have another question. So do you ever see actual bifurcation? Because these are just limit points, right? Do you see actual bifurcations?
Not yet. All
this
the
type of fast-following simulations?
No, all of the simulations that we've done so far have been of this type, but the method is general enough that we could capture more complex bifurcations. Is that right?
That's the long-term idea, to use this numerical continuation and variety of setups in atomistic modeling.
Okay. There was a question in the middle at the back, and then that one maybe. Yeah.
That's it. You go ahead. So that's sort of the opposite question about, I mean, I understand that things can be, or if you're discontinuous and you go downhill, but I'm happy with a smooth path. But
No. It's not very smooth. That's because we're using quite big steps along the solution path.
Are you sure the potential is smooth, right?
Sorry?
Are you sure that the potential is smooth?
No, not necessarily. The potential might not be completely smooth in this case. I'm also not correcting quite as well, so the tolerance on the optimizations that bring you back to the path is a bit looser in order to get this to work fast. The one I showed for silicon is super smooth, partly because the potential is smooth, but partly because I'm converging very well at every step. This is a very new result, so I was keen to share it, but it's work in progress.
I think there's some minor issues with implementation around the boundary region, which needs fixing, and hopefully that will make it all smooth, because the subtleties about, like, if you move the alpha a little bit, perhaps some atoms jump out of the interaction range, and you need to capture that fully when you differentiate with respect to alpha. So hopefully in a year from now that will be really smooth. That's the hope. Perhaps not.
Question at the back.
So I'll go back to the previous one. So this is, you're just testing whether you're able to do the path following continuation? Not, because in reality this won't happen. I mean,
no, that's right, but what it gives us insight into is the range of stability for real cracks. We can map out K plus and K minus, the stress intensity factor range over which fracture is stable. And we can also read off energy barriers so that we can make predictions for speeds of kinetic crack growth at low temperatures. So we can get real observables from this technique, and it's much more convenient than...
The energy barrier you could just get from a stable grid. But I think you answered my question. You don't necessarily have to go through the unstable bit to get that.
No, I don't know if you've tried to do these calculations. They're very fiddly to set up if you don't have something that can follow these paths. Because, as I've said, the solution jumps.
It should. I mean,
right, which makes it hard to calculate the barriers. And so it's really nice to have something where the barriers come out directly, all K, right? So as a function of K, we can just read off barriers from this single calculation.
Yeah, I mean, for that, for the barrier, you don't necessarily need this unstable bit. I mean, on the stable bit, if you get the height?
The transition state is the unstable part of the diagram. So for crack advance, we move from stable to stable via a saddle point, and the saddle point is the unstable part of the solution path.
So it's not just the difference between two stable states. There's a barrier in between.
Yeah.
Like if
Sure.
Okay, I think we should probably move on, or I'm not going to get through the other things I wanted to talk about, but it's great that it's excited some interest. So I wanted to talk also now about hierarchical coupling. So mostly what I've said so far has involved bidirectional coupling. It's great that you can do that when you need to, but you really shouldn't if you don't. And the first examples are on interatomic potentials, so building on what we heard from Gabor earlier on. This is fracture using the silicon gap that we developed over many years. And just as a brief reminder, I think we don't really need it after Christoph's talk as well, but the idea is to use DFT to learn weights and then parameterize models by comparing configurations. This is a Gaussian process regression framework, so we're comparing configurations to a set of reference configurations rather than putting all of the information into the coefficients, but it's very much the same idea. I wanted to briefly mention another gap that has been fitted in my group by Harry Tunstall, just to show kinds of things that you can do. So this is multi-species, two species, it's silicon carbide. And what we were pleased with here is that we could quench it very quickly. So we could go from 3000 Kelvin down to 300. And in that case, we get the blue curve, which matches up rather well with the density functional theory radial distribution function that characterizes the structure of the amorphous, because in DFT you have to do it fast. You can't afford to do a super slow quench. However, once we have the machine learning model, we can afford to run it much more slowly, and we can cool down more realistic speed. It's still rather quick compared to experimental quench. And then we start to see a better agreement with the experimental structure. So it opens the door to doing new things with these models. Jan?
Maybe one more question. How do you construct the training sets for building these models? Because
that isn't a question I can answer and finish the talk on time. That's a lunchtime question.
Okay.
But maybe we'll get some things about that. But I wanted to recap some of the things we've heard about challenges with using these models. So one of them is incompleteness. We've heard about how using higher order features can help to address that, so I'm not going to say anything more about that. Another is how we can model many chemical species without the quadratic scaling of descriptor length with respect to species that we heard about from Gabor. And again, I'm not going to say anything more about that because the compression strategies that he outlined are a good way forward there. What I want to briefly talk about is how we can use very large training sets and how we can improve uncertainty quantification. So thinking first of all about the large training sets, the way that we actually fit these gap models is to solve a linear system. We don't actually use all of our data points as basis functions, as features. We select a subset of them, maybe a few thousand compared to potentially a few million training points, and then we solve a sparse Gaussian process or a kernel ridge regression problem, which corresponds to a linear system. It's a least squares problem, essentially, and we solve it by QR factorization. So that's what you actually do in order to solve this operationally. And the challenge is that this matrix A is very, very large if you've got a lot of observations. And that was limiting the scalability of the approach to very large training databases. You needed to have enough memory to store this matrix and then enough time to be able to do the solve. And people were using multi-terabyte compute nodes in order to do that. What we've done is take that big matrix and split it up into pieces so that you can do this solve in a distributed way. That helps you in two ways. First of all, you can parallelize trivially over the evaluation of the descriptors. So filling in this matrix is much faster because you can do it in parallel. And it also helps you because you don't need to store it all in one place. So you can use your entire HPC facility's memory. You don't need all the memory on one node. The scaling is pretty good. So we get to 5,000 cores or so with quite a good speed up factor, 40 or 50. And that takes the time to train one of these models with millions of configurations, like the silicon carbide example I just showed you, down from a few days to maybe a few minutes. And that opens the door to new ways to do things as well. You can start to actually think about how to optimize hyperparameters, how to do high throughput models, how to think more about uncertainty. So I think it might actually be quite useful. I should say this was done in the context of the NOMAD project, where the idea is to make these kinds of techniques more widely accessible. So there'll be a web interface where you can go, you do a query on the NOMAD archive, which is a repository of uploaded DFT configurations, and then you'll be able to fit your own model and download it. That's the aspiration by the end of the project. If we look at the breakdowns of the timings, we can see, as I said, the descriptor evaluation is trivially parallelizable, so that really does just speed up linearly as we increase the number of cores, whereas the linear solve becomes the bottleneck eventually, because we have to do quite a lot of communication to do that linear solve. And that motivates potentially moving to an iterative solution scheme in future that would allow us to completely parallelize effectively over that as well. Okay, coming to the second thing I wanted to talk about in terms of machine learning potentials, which was uncertainty. A little bit more detail on how we predict uncertainties at the moment. So we interpret the Gaussian process, interpret the kernel ridge regression as a sparse Gaussian process, and then there's a formula for the posterior variance estimate at a new point, which we can use. It involves comparing the configuration of interest to all the reference configurations. And this is what that looks like for vacancy diffusion. So here we have a good agreement between vacancy minima, and so the predicted error and the true error are both quite low, whereas at the saddle point, it wasn't as well represented in this particular training database. The true error is bigger, and the predicted error is bigger as well, but there isn't a good quantitative alignment between the two at this stage, and that's for a couple of reasons. It's because this statistical error estimate is sort of conflating different sources of uncertainty, in particular parametric uncertainty on the coefficients of the model, the kind of hidden coefficients in this Gaussian process, but they are there. and epistemic uncertainty, so limitations in the model at the cutoff of the interaction, the limited body order of the representation. We're sort of mixing all those together and treating them as statistical error. And then also, as we add more and more data, this uncertainty has to go to 0. So it can't really fully capture the remaining uncertainties in the problem. So what we wanted to do was look if there was a way to rescale the error estimates that we get out of these kinds of statistical methods in order to get better alignment with true errors. And we came across this method called conformal prediction. I hadn't come across before, but it's quite appealing. It's quite easy to apply. So what you need is a score function that should be some sort of probabilistic output. You need a surrogate model that gives you a mean and an error estimate, and you need some calibration data. We have all those things. And then what you get for it is you use all of these scores and you compute a rescale factor that you apply to the error estimates that come from your existing model, and you have actually a guarantee, a formal guarantee, that the true solution lies in this range under some reasonable assumptions. It is a guarantee, but it may not be useful, because what could happen is that you get a very big Q-hat if you don't have a very good score or very good calibration data. So you might get error bars which are formally contain the true answer, but are very large. We wanted to try it out and see if that's what happened or if it was actually useful for us. So the setting is the Bayesian linear regression interpretation of the ACE model that Christoph described earlier. So that's really just a linear model with some basis functions. These are the final output of all of the processes that Christoph described, the B basis. And our model is just a dot product of some coefficients in those basis functions, and then with some error. As I said, we have to assume that that error is Gaussian if we want to make analytical process with the error estimates. And then we can just use Bayesian linear regression, which corresponds to ridge regression, but gives us a nice way to think about the priors on the hyperparameters. Yep.
Any good justification for the covariance matrix to just be identity?
No, not really, and one could do better. So this is just standard Bayesian linear regression. You can do better than that if you have some more ideas about what the covariance, true covariance should be. Yeah. But it's a reasonable starting point. Yeah. Again, if we want to make analytical progress, we need to use a Gaussian also for our prior on our coefficients. This is the very simplest choice where we just have one precision that goes with all the coefficients. You can do something called ARD, where you have a different alpha for each basis function, but we haven't tried that yet in this scheme. If you have Gaussian prior, Gaussian likelihood, and a linear model, then everything is analytic, and your posterior is also a multivariate Gaussian. You can just write it down, and you can draw samples from it, and that's what's used to generate a committee of different models that are all compatible with the data. There's a slight detail about how you choose these coefficients. We did it in a Bayesian setting by finding the parameters which maximize the evidence. So that's the probability of the data given fixed choices of the hyperparameters, and you vary the hyperparameters and maximize that guy. That's a difficult optimization to do, and we found to have something robust that worked well, we had to use particle swarm optimization. So lots of different agents trying to maximize that and communicating with one another. But that's a bit of a detail. So then we get this Gaussian posterior. We can draw samples from that to get a committee of models, similar to what's done in hyperactive learning, if you've heard about that from Gabor or Christoph or Kaz van der Rohe before. And then the new ingredient will come at the end. We take the mean and the standard deviations that come from averaging and computing deviations across this committee, and we just rescale them by this factor that comes from calibrating on similar kinds of data. So we hold back some of the training data and use it for calibrating the uncertainties. So we've applied this to the same silicon database that you've seen lots of times, and we did it for a range of, the axis label has gone there. This is varying the amount of data, and this is varying the maximum polynomial degree. And we can see that as you add data, or as you make your model more accurate, these error estimates go down. If we take a slice through that data here, we can see that as we increase polynomial degree, this is for a quantity of interest now, so we take these committee members and we evaluate something with them, in this case the bulk modulus, which is quite a straightforward thing to compute. So as we increase the quality of our basis, the model does get more accurate, but also the error estimates get better. And then because of this nice coverage property, the error estimates do cover the true answer. Christoph?
It's only the estimates, not the true errors.
You can see the true error by comparing the crosses with the blue line in this case.
Oh. So they actually, the order of magnitude is
Yes, because of the
much too big initially, but then eventually
they're
not.
That's right. So this is where you see the conservative aspects of the conformal prediction, but they do all cover, all the error bars hit the blue line,
But then in the
more
end,
or
you
less.
start overfitting somewhere.
That's right. So the evidence does actually peak about here. And so,
Consistent with everything.
Yeah.
Experience.
Yeah.
Thank you.
Yeah. Yes, they're just 2 sigma error bars. I'm just using the conformal predict. No, you don't. It's distribution free. You just get a number, a rescale factor. I just apply that rescale factor to the error predictions that I get from the Bayesian linear regression. Okay. We've also applied this to varying the amount of data. So looking, Gabor.
But your actual error is independent.
It's getting a little bit smaller. These guys are overfitting, yeah.
Max degree of 3, and you still get the right, your model still gets the right model. Is this because the Barton universe is just such a simple thing?
I think so, yeah. So let's look at the next example, which is a little bit more difficult, but we haven't really pushed the limits of this yet. This is elastic constants, C11, C12, and C44, versus amount of training data. So if you don't have much training data, they're really bad, but the error estimates know that they're really bad and do cover the true error. And then things stop improving after you have more than 100 configurations, which is what you'd expect, but it's nice that that's also reflected in the error estimates. Okay, I've only given myself 5 minutes to talk about the last topic because we've had quite a bit of discussion as we go along. Can I beg 2 extra
Well,
minutes?
I'll give you 2 minutes
Yeah.
too, we're gonna be fair.
Yeah. So we got 7 minutes to talk about fitting Hamiltonians. But the good news is there's no new maths because it's exactly what Christoph presented earlier on. So I can focus on the application side. So the idea here is to try to learn electronic structure, to go down 1 level from what we've been doing so far and try and learn Hamiltonians from density functional theory data. We use a local orbital density functional theory code, FHI-AIMS, and we build a database of Hamiltonian matrices and actually overlap matrices as well, so we can work in a non-orthogonal setting. So this is a type binding type model, except that it goes beyond type binding in that we no longer have the 2-center approximation. So we include all interactions, and in particular, we include the so-called crystal field terms, which are the off-diagonal parts of the on-site blocks in the overall Hamiltonian matrix. So this is the overall matrix. These blocks are on-site. That means interactions between 2 orbitals sitting on the same atom. Off-site is orbitals on 2 different atoms. These guys, the on-site ones, are very similar to an interatomic potential. There's an equivariant transformation of these blocks that depends on the particular angular quantum number of the orbitals that are involved. So if you're looking at a PP block, then you need to use the relevant Wigner-D matrix here. But we know how the blocks transform, and we can use that to build appropriate representations that are equivariant to that symmetry. The on-site blocks are a bit like a potential. We want to learn them as a function of a spherical environment centered on an atom, because that's what's relevant there. And so we can do that using an ace basis similar to what Christoph described. The off-site blocks are a bit more involved. Now we're thinking about a bond, so it's the environment of a bond that matters, and we parameterize that through the bond vector, and then also through the cylindrical environment surrounding a bond. Now we basically do a very similar idea. We integrate over the symmetry group in order to have something which has the correct transformation. What we get out is very much the same spirit as the interatomic potentials, a linear model for the blocks of the Hamiltonian. And then we can put them together to get an overall linear model for Hamiltonian and also for overlap. So we evaluate these B basis functions and we multiply them by some coefficients and we get our models. We need to fit those coefficients. We do that in just the same way as was described earlier. So it's a least squares fit to training data. The training data are now matrices, but apart from that, everything is pretty much unchanged. So we do a regularized least squares fit. There's a regularization going in there of a smoothness. And then when we want to make a prediction, we need to send our atomic positions, evaluate the basis functions that correspond to those positions, and then just do a dot with the coefficients that we've obtained from the parameter estimation. That gives us back Hamiltonian and overlap. We still need to do an eigensolve. So overall, it's still a cubic scaling method. We haven't skipped that part, but we get to skip the self-consistent field iterations that you have to do at the earlier stages in DFT. We jump to the point where you're diagonalizing. In principle, might be alternatives to doing that. We had some interesting ideas this week. how well does it work? We'll first look at the accuracy on the Hamiltonian itself. So in the on-site blocks, we get pretty good accuracy as we increase the size of the basis set, the maximum polynomial degree. Dashed lines here are held back test set, and solid lines are a training set. They're all going down without too much overfitting. For the off-site blocks, the bonding blocks, we do get a bit of overfitting, particularly for the s orbitals. They're very smooth. We shouldn't be using very high order polynomials to describe them. So we have to truncate that basis somewhere there and not use these things where test is getting worse while training continues to improve. And actually we stop at correlation order 1, which for a bond model, right, we've got 2 atoms in the bond, 1 in the environment, is already body order 3. We stop there rather than going to the next order where we get significantly worse overfitting. If we propagate those Hamiltonians through and use them to compute band structures, they actually look pretty nice, and they improve systematically as we increase the size of the basis. So this is a band structure for FCC aluminium. We didn't include the crystal ground states for FCC or BCC in the training database, so this is a bit of a test of transferability. We only included MD data, so where the atoms were away from equilibrium. And you can see both the band structure, certainly for the occupied parts of the band diagram, and also the density of states, converge quite nicely as we add, as we increase the size of the basis set. Same thing for BCC, maybe not quite as accurate, but again, up to the Fermi level, it's well described. And similarly for the density of states, up to the occupied part of the spectrum. This is just showing the same thing. So if we make some choices about where to cut off the size of the basis separately for each of the different blocks in the matrix, we can come up with an overall model that doesn't overfit and that works well. And these are the predictions that we get from it that are in good agreement with reference DFT calculations. So far, that's not really showing extrapolation, so we want to try something a bit more challenging. We fit this model to aluminium in the FCC state and the BCC state, which are 2 ends of what's called the Bain path. So it's a crystal transformation where we can shear our cell and move from one crystal structure to another. Without refitting or changing anything, we just evaluated the model along that path and checked the errors in the bands and in the density of states, and they all came out pretty well, suggesting nothing crazy is going on at least. Then there's a bit more of a challenging test. We'd only trained this model on bulk, but we wanted to see how it would perform on a defect. The training data was 500 Kelvin MD, so atoms were jiggling around a little bit. And actually, when we put a vacancy in and made a prediction for the projected density of states, so a probe for the electronic structure for the nearest neighbors of that vacancy, and they come out pretty well. So blue and red here are comparisons between the ACE prediction and then a DFT test. And the green is showing you what the plain FCC structure without any defects looks like. So there is quite a shift in the density of states, and we don't quite capture behavior at the Fermi level itself, right? But for the lower levels, and that shift is, those changes are quite well described. Okay, I'm definitely running over my 2 minutes now, so this is my last slide. We've recently cleaned up the code and released it, and we hope that it's starting to be potentially useful for other people. As part of that, we tested it in a new system, which was silicon. So once you've done aluminium, the next most simple thing you can try is silicon, but that's also working pretty well and is giving a good description of the band structure for quite a few of the unoccupied bands as well. Okay, I had a few discussion points. I think a few of them have come up already, so I will probably just go through them quite quickly. Is there anything that is here that hasn't been said by other people? No, not too much. I want to thank everybody who contributed in my group, Petter and Tom in Marseille, Li Wei and Christophe, Geneviève, who contributed to the Hamiltonian's work, Tom and Andy, the experiments, and Gabor also in Cambridge, and Maciej, the flexible boundary conditions. Gautam also worked on the Hamiltonian work. And then very briefly advertise that we've got an opening for an assistant professor position in the group that I lead in Warwick. If you're interested in that, have a chat to me at some point later on. We've also got a couple of PhD openings. Thank you very much.
Great.